The power of quantum computing, why it outpaces classical computers. Quantum computers are fundamentally different from classical computers, and this difference allows them to solve certain types of problems much faster than classical computers. In classical computers, a bit is the basic unit of information, and it can represent either a 0 or a 1. These bits are processed sequentially by the computer, one after the other, to perform computations. For example, to add two numbers, a classical computer would perform a series of bit-level operations, one bit at a time. Quantum computers, on the other hand, use quantum bits or qubits. A qubit can represent not only 0 or 1, but also a superposition of both states simultaneously. This means that a qubit can exist in a combination of both states at the same time, which allows a quantum computer to perform multiple calculations simultaneously. This is because quantum mechanics allows for the phenomenon of superposition, which means that a particle, in this case, a qubit, can exist in multiple states at the same time. For example, a qubit can exist in a superposition of 0 and 1, which means that it represents both 0 and 1 at the same time with a certain probability. To perform a computation, a quantum computer can manipulate the qubits using quantum gates, which are analogous to the logical operations in classical computers. By manipulating the qubits in parallel, a quantum computer can perform many computations at the same time, potentially leading to much faster computation times for certain types of problems. It's important to note that measuring a qubit collapses its superposition into a single classical bit value, so the result of a quantum computation can only be obtained by measuring the final state of the qubits. This process is probabilistic and may require multiple measurements to obtain an accurate result. Classical computers typically use algorithms that rely on the fact that factoring large numbers into their prime factors is a computationally difficult problem. This difficulty is since classical computers must perform the factorization sequentially, trying all possible factors one after the other until they find the correct ones. Shor's algorithm is a quantum algorithm that is exponentially faster than any known classical algorithm for factoring large numbers. This algorithm takes advantage of the quantum mechanical properties of qubits, which can exist in multiple states at once and be entangled with each other. Shor's algorithm consists of two main steps. The first step involves using a quantum computer to create a superposition of all possible factors of the number to be factored. This is done by applying a quantum Fourier transform to a register of qubits. The result is a state that contains all possible factors of the number, with each factor having a different probability. The second step of the algorithm involves using a quantum computer to measure the state of the qubits and extract the factors of the number with high probability. This step is performed using a classical algorithm that processes the output of the quantum measurement and finds the correct factors of the number. The advantage of Shor's algorithm is that the first step can be performed in parallel on a quantum computer, allowing all possible factors to be considered simultaneously. This makes the algorithm much faster than any known classical algorithm, which must perform the factorization sequentially. Overall, Shor's algorithm demonstrates the potential of quantum computers to solve problems that are currently intractable for classical computers, and it has important implications for cryptography and other areas of computer science. Entanglement is a phenomenon in quantum mechanics where two or more particles become correlated, so that the state of one particle depends on the state of the other particle. In the case of quantum computing, entanglement can be used to perform certain computations exponentially faster than classical computers. One example of a computation that can be accelerated by entanglement is the problem of searching an unsorted database. Classically, this problem requires searching through each item in the database one by one until the desired item is found, which can take a long time for large databases. However, a quantum algorithm called Grover's algorithm can use entanglement to search an unsorted database with only a few iterations. Grover's algorithm uses entanglement to amplify the probability of finding the desired item in the database. The algorithm first creates a superposition of all possible items in the database, then applies a series of quantum operations to amplify the probability of finding the desired item. The entangled qubits are used to create constructive interference between the correct item and all the other items in the database, which leads to a quadratic speedup over classical algorithms. Another example of a computation that can be accelerated by entanglement is quantum simulation. Quantum simulators are devices that use quantum mechanics to simulate the behavior of complex systems, such as molecules or materials. Classical simulators can be very slow for complex systems, but quantum simulators can take advantage of entanglement to simulate the behavior of the system much faster. In general, entanglement can be used to perform certain computations that are exponentially faster than classical computers. These computations take advantage of the fact that entangled qubits can represent multiple states at once, which allows them to process information in parallel and perform certain computations with a speedup over classical algorithms. It's important to note that quantum computers are not necessarily faster at all tasks than classical computers. They are optimized for certain types of problems and may not be as efficient for other tasks.